Okay, hi everyone. This is our video where we are doing more linear classification. We're going to do linear classifiers with a gradient descent. So the gradient descent, and again, if you haven't watched the lecture or gone through the slides, you should do that first. This is just the Excel part. But remember, the gradient descent is updating our parameters in order to minimize an objective function, and we're doing that using the derivative or the partial derivatives of that objective function. And so what we need is our objective function, which is based on two parts. It's based on the loss function, which we're going to have here in the Excel sheet, and it's based on the regularization term, which, if you remember from the lecture, is all about pushing out our margin boundaries to see if we can't get that line as far away from the training data as we can, because we want a nice evenly spaced line. So the first thing I'm going to do is I'm going to put in my Z. Now my formula for Z, if you remember what we did last week, this is the same thing. This is the Y times that brackets thing, right? So we're going to do Y times, and then in brackets, we're going to do theta1 times x1 plus theta2 times x2 plus theta0, right? That whole thing in the brackets there, that's what we get when we plug our x values into the line. And the whole idea is that when we multiply by y, if the result is positive, then we have correctly classified, and if it's negative, we have incorrectly classified. So we are going to calculate the loss function based on this. So our loss function goes like this. It's an if statement. If z is greater than 1, there is no loss. But if z is less than 1, then we are too close to the line or possibly misclassified, and we have some loss. What's the loss going to be? It's just going to be 1 minus z. So that's our loss function. And then we need to do the updates for theta, for the thetas. I'm going to do theta 0 first because it's the easiest. It's similar to last week. But we had this eta going on, and this eta is going to be different from last week. So let's see. The way this works is now we can do if the loss equals 0, or we can do if z is greater than 1. It doesn't really matter. They're the same condition. Right? If the loss is 0, if there's no loss, then what's our update to theta 0? Well, there's no update essentially. We're just taking our same old theta 0 as before. Right? If there's no loss, theta 0 does not change. If there is loss, right? So if the loss is not 0, then what's going to happen? Our theta 0 is going to update. Now, if you remember what happened last week, it was theta 0 plus y, but now we need to take that y and multiply by eta. The eta is shrinking, and the idea here is this is just going to shrink our updates over time to make sure that they converge, because we could potentially have a problem where the updates will not converge and our line will keep on wiggling back and forth between two different positions or something, right? We could have non-convergence if we don't shrink our updates. And so that's why we have this eta, which is going to get smaller with each step. Right, so far, this new theta 0 is the same as perceptron, right? Except that we have this eta thing to make sure it converges, because we don't want to have the thing with perceptron where we have to wait for it to be done. With perceptron, we had to wait until all the points were properly classified. Here, we don't want to wait for that because we know that it's not always going to be possible. So we are just going to force this to converge at some point. So that's theta 0. Theta 1 and theta 2, a little bit more complicated now. So because they have to deal with not just the loss, but also the regularization. And the regularization is going to depend on this lambda value here. This lambda value is the regularization parameter, and its job is to say how important is regularization relative to loss. When lambda equals 0, we're saying that we don't care about regularization at all. Loss is the only thing that matters. Of course, if lambda went up to infinity, then regularization would be the only thing that would matter, and loss would not matter at all. Right? So with lambda equals 0.5, we're somewhere in the middle. Regularization matters, and so does loss. So just, each to their own certain amount. So what's theta going to do? Well, same idea to start with as theta 0, right? This is if the loss is 0, then we're not going to have to do as much. If there's no loss, then the only thing we're going to do is the update based on the regularization and not based on anything else. So we're going to take the theta 1 from before, and what are we going to do? We're going to shrink it a little bit. We're going to subtract lambda times theta 1. So we're taking our theta 1 and we're subtracting a fraction of theta 1, right? In other words, we're just shrinking it. We're shrinking it by a predetermined amount. In this case, lambda equals 0.5. So we're taking theta 1 and we're shrinking it by 50%. And that's going to, and by shrinking the theta 1 and the theta 2 by 50%, that's going to push our margin boundaries out. We're going to essentially double the width or something like that. But we also need to include eta. So there's eta. Eta is involved here. Right? Because of course we need convergence. So that eta is going to force it to converge. That's if there's no loss. On the other hand, if there is loss, the update gets more complicated. What's the update going to be now? It's going to be the old theta 1. And then what are we going to do? We're going to subtract. Now in brackets here, I'm going to have in brackets because I'm going to have the regularization part and the loss adjustment both being multiplied by eta, right? So in brackets here, I'm going to have the same regularization part, lambda times theta 1. That part's the same, but we're also going to have minus the y times x1. That y times x1 should be familiar from last week from perceptron. This is the same adjustment as perceptron. So we're doing the perceptron adjustment and we're doing the regularization adjustment, and then we're multiplying those both by eta so that we know it will eventually converge. And this is what our formula looks like. We need to make some of this static, in particular lambda. Lambda needs to be static, right? Because lambda's only here, right? Lambda doesn't go down. The etas are going to go down. Everything else is going to go down. Lambda's only in one spot. So that lambda's got to be static. This is our formula. And we can leave it like this, and we can copy and paste it down, and this is all good. But if we want to type it in, if we want to do theta 2, we're going to have to type it all in again. Right? Type in the same thing all again, except everywhere there was a theta 1, now we're going to have a theta 2. Everywhere there was an x1, now we're going to have an x2. You have a couple of options to do that. One option, I'm going to show you 3 ways to do this, and you pick whichever one you like best. One way to do this is copy the cell over, and then in here, everything moved, but we don't want all of it to move, right? Theta 1 moved to theta 2. That's good. We like that. Loss moved over here to theta 1. That's bad. We don't want loss moving. Y moved to Z. We don't want that. X1 moved to X2. That is good, but eta moved to X1. Whoops. It did that twice, and we don't want that, so we're moving those back. So one option is you copy the cell over, and then you move back the things you didn't want to move. In this case, it's very important to know what's supposed to move and what's not. The only things that are supposed to move are X1 is supposed to go to X2, and theta 1 is supposed to go to theta 2. Nothing else is supposed to move. So that works. That's one option. I'm going to show you the next option. The next option is I'm not going to copy the cell. I'm going to click in here, and I'm going to copy the formula. Control C on the formula, and then Control V. And now what's happened is nothing has moved, and I'm going to manually move the things I want to move. So the X1 should move to X2, theta 1 should move to theta 2, both times. In fact, all 3 times. 4 times, however many times theta 1 is in there. It's in there a lot of times. So we're going to move them all over and hit enter, and there we go. That also works. Those are your 2 options. Third option is in here, if we just make the things we don't want to move partially static, we can't make them fully static because we want them to copy down. But if we just fix the columns, that'll be fine. So H4 is the loss. We don't want that to move. So I'm going to fix the column H. I3, that's theta 1. I do want that to move over. So I'm going to leave that. I3 is I'm going to leave that. C4, that's the eta. I don't want that moving. I'm going to fix it. I3 is theta 1. That can move. I3 is theta 1. That can move. F4, that's the Y. That shouldn't move. D4, that's X1. That should move to X2. And then C4 is eta again. That should not move, right? So I'm putting dollar signs on the columns that should not move. And now I can Control C, Control V, and that works. This one is nice because if you have a lot of thetas, right? In this case, we only have theta 1 and theta 2, but if we had theta 3 and theta 4 and theta 5 or whatever, we would just have to put the dollar signs on once and then copy the whole thing over, and that would work real good. So that's a really nice way to do it. That's probably the best way to do it. But you do have options and you can do whatever one works for you. Anyway, all our formulas are done. We can copy and paste them all down now. And we get our updates happening. So when we have loss, we make some updates. When we don't have loss, we still make updates because we're doing regularization, right? Just less, right? So when we have loss, the whole line is shifting and rotating, totally different line, right? But then when we have no loss, the line does not shift and rotate. The theta 0 stays the same. And the theta 1 and theta 2, they just shrink a bit. Okay, so that is how we are updating our thetas based on our objective function. And we're applying our objective function to just that one point at a time, because what we're doing in this case, like I said in the lecture, is a stochastic gradient descent. That means we're just sampling a random point each time, rather than calculating these derivatives for the whole thing. Okay, so then what we're going to do is we are going to, we could keep going, but now what I want to show you is how do we keep going, right? How do we keep going? Well, the t's just keep going and increasing like that. Right? If you want to use if you want to just type 1, 2, 3 and then click and drag the corner, that works in Excel. If you want to use a formula, you could use equals this plus 1 and then copy and paste down. Right? That works too. A couple of ways to do it. Anyway, eta is based on a formula. Remember, eta's job is just to shrink. Eta just has to shrink over time slowly. So eta is going to be 1 divided by brackets 1 plus t. That's all eta is going to be. And like I said, it just has to shrink. So we can see it's shrinking towards 0, never actually reaching 0. That's what eta is supposed to do. And now we get to the random points, right? This is stochastic gradient descent. Stochastic means we have randomness over time. And so we are going to randomly be selecting a point from this list of 12 points. The formula you need to do that is rand between. Rand between picks a random integer between the numbers you give it. So we are giving it the number 1 and the number 12. Rand between 1 and 12 will pick a random number between 1 and 12. So there we go. I can just double click that down. Now you have all these random numbers. Every time you update any cell, if I type something here and hit enter, or if I just hit the delete button, anytime you update that, all these numbers re-randomize. Maybe you want that. Maybe that's good for you. Maybe you don't. If you don't want them to keep on re-randomizing, if you just want to have one sample and stick with it, then what you're going to do is you're going to highlight all of those, Control C to copy, and then right click, paste values. Now they're locked in, right? They're still randomized because you randomized them, but they're locked in. They're not going to keep updating. The constant updating can really slow your Excel down if you have a lot of rows, right? We're only going to have like 100 rows. It wouldn't be a problem. We could have left them re-randomizing and it wouldn't have been a big deal for us. But if you had 10,000 rows or whatever, then every time you adjusted any cell, it would re-randomize and have to recalculate like 100,000 cells or something, and it would be slow. So now what we need to do is we need to translate these random points, right? Random reference numbers. We have 12 reference numbers into these x1, x2, and y. And we're going to do that with a vertical lookup. So the formula is VLOOKUP. It's a vertical lookup table. And the value we're looking up is the random value we picked. The table we're looking it up on is here. And that needs to be static because that's never moving. And then what column are we looking in? Well, for x1, we're looking in the second column. And this is how our VLOOKUP formula works. Now, with VLOOKUP, it's important that the numbers you're looking up are in the first column. So this table has to be laid out like this. If you laid out the table x1, x2, y, and then the reference numbers on the right, the vertical lookup formula wouldn't work properly. Right? It always looks in the first column for whatever you're looking up. So it's looking in the first column for the number 7, and then it's going to return whatever's in the second column. So it should return -5 when I hit enter. And it does. So that's good. I want this to move over, but when I do that, I don't want my column moving. So I'm just going to fix that A7, but not fully static because I want it to copy down. I only want to lock the column, not the row. And so now I can copy and paste that over. And all I need to change here is change the 2 to a 3 because I want the third column for x2. And then change the 2 to a 4 because I want the fourth column for y. With that done, and then copy pasting this down, I now have everything ready to go. This whole thing can just copy and paste all the way down, and I get updates all the way down, as many rows as I like. And there you go. So that's how we're doing the stochastic gradient descent, where we're selecting these random points and adjusting based on those. So the two parts we learned today were how to randomize the points and put them in using a vertical lookup table, and also how to do the actual updates using the gradient descent method for this particular objective function. Right? If you change your objective function, you change your updates because the updates are based on partial derivatives. So if you want to apply this to a different function, then and you will, right? In the real world, if you're using gradient descent, you can use it all over the place. It works on all sorts of functions. You just need to have a little bit of calculus to do some partial derivatives on your objective function to figure out how to update your parameters. There's lots of different tweaks you can do to it. The eta can be tweaked a little bit, right? Eta's job is to shrink. We're shrinking it in this specific way, but there are other ways you could shrink eta faster or slower slightly to get slightly different results, depending on what you're interested in. The other thing is, I mentioned in class, or at least in one of the sections, I don't know if I mentioned in the other, but for those of you who didn't catch this, there's some terminology that you might see. SVM, support vector machine. That is another name for essentially what we're doing here with linear classifiers, right? If you see support vector machine, that's talking about making a linear classifier like this, right? There's just a lot of terminology, and a lot of the times you'll have different terms that refer to the same thing. So if you hear someone talking about something that you've never heard of before, well, maybe you actually have heard of it, just under a different name. So there's that. If you see people talking about support vector machines, you know more or less what they're talking about. They're talking about things like this. Okay, so that's it for this video, and see you all in class next week for our midterm review.